when you watch someone teach a young child how to write their letters for the very first time, there is this almost obsessive focus on the grip. Think back to it.
Oh, yeah. The classic tripod grip.
Right. The teacher or the parent kind of hovers over the desk, physically adjusting those tiny, totally uncoordinated fingers around this comparatively massive pencil.
Trying to force them into that one specific shape.
Exactly. Thumb here, index finger resting just so. The shaft of the pencil resting exactly on the middle finger.
And if the child deviates from that exact physical configuration, say they use a full fist grip, or they tuck their thumb underneath their index finger.
Which they always do.
Right, they always do. Or if they hold it completely vertically, the immediate reaction from the adult is usually correction.
Always. No, hold it like this.
Yeah. Even if that child is somehow managing to drag the graphite across the paper and draw a perfectly legible, perfectly proportioned letter A, they are inevitably told they're doing it wrong.
It's so wild when you step back and look at it, because we completely conflate the ultimate goal with the specific physical mechanism of getting there.
We really do.
Because, the actual goal is just creating a legible, transferable form of communication on the page. That is literally it.
Right.
But instead of prioritizing the outcome, we demand physical mimicry. We essentially say, hey, to achieve the result that I achieve, you must move your muscles and bones exactly how I move mine.
Which is, frankly, an incredibly limiting way to look at teaching.
It really is.
Because it assumes that there is a singular, optimized physical path to a goal, completely regardless of the physical differences in the agents performing the task.
Yeah, like hand size or whatever.
Exactly. If a child has smaller hands or different muscle tone or, different fine motor development, the quote-unquote standard tripod grip might actually be highly inefficient for them.
But we enforce it anyway.
We enforce it anyway. And while that might just seem like a quirk of early childhood education, that exact same assumption is everywhere.
And it has fundamentally crippled the development of artificial intelligence and robotics for, the better part of 60 years.
It's been the massive roadblock, yeah.
So today we are diving into a breakthrough that finally shatters that assumption. And for you listening, if you are always looking for those rare aha moments that connect disparate fields without getting bogged down in impenetrable jargon, this is the deep dive for you.
It is a totally fascinating topic.
We are looking at a landmark paper published in Science Robotics on March 18th, 2026. It's titled Cross-Robot Behavior Adaptation Through Intention Alignment.
Quite a mouthful.
A bit of a mouthful, yeah. But we're also pulling from some deep analysis from an excerpt called The Portability of Intention, along with some supplementary reporting from TechExplore and phys.org.
Yeah, and the core premise here, the thing that really shifts the paradigm, is a beautifully simple question.
Right. What happens when you realize that teaching a machine a complex skill doesn't require it to mimic another machine's movements?
What if it doesn't even need to have the same kind of body?
Exactly. What if all it needs is to understand the aim?
It completely rewrites the equation of machine learning. And, by extension, it actually challenges our entire philosophy of collaboration.
Which we're going to get into because that part blew my mind. But to really grasp the mechanics of how this works, we have to examine the historical baseline first. Right?
Yeah, we have to look at what the field calls the embodiment gap.
The bottleneck of likeness.
Right. For decades, the entire foundation of robotics has been built on this absolute bedrock of physical sameness.
Let's trace that back a bit. If we look at traditional robotics, from the earliest animate arms in automotive factories in the 1960s, all the way up to the highly advanced reinforcement learning models of the early 2020s, the architecture of learning was always explicitly tied to the architecture of the hardware.
Precisely. In robotics, an action is defined by kinematics.
Okay, unpack kinematics for us really quickly.
Sure. So if you have a robotic arm, let's say a standard industrial manipulator with 6 degrees of freedom, that basically means it has 6 different joints that can rotate or pivot.
Got it. 6 joints.
Every single movement it makes is mathematically plotted in what we call configuration space. When that specific arm learns how to, for example, pick up a fragile glass without breaking it, the quote-unquote knowledge of that skill is encoded as a highly specific series of joint angles.
Angles, torques, motor velocities.
Exactly. It's a mathematical symphony, but it's written exclusively for an instrument with exactly 6 joints of those exact dimensions.
So if that robot figures out the absolute optimal way to pack boxes in a warehouse, and the engineers want to scale that efficiency up, they historically had to go out and buy 100 more robots that were identical down to the millimeter.
They had no other choice.
Right, because if they tried to transfer that knowledge to a completely different model, say a robot with 7 degrees of freedom instead of 6, or maybe one with a mobile base or a parallel gripper instead of a multi-fingered hand, the code is basically gibberish to the new machine.
It is worse than gibberish, honestly. It is computationally hostile.
Hostile. How so?
Well, the instructions literally do not map onto physical reality. A command that says, rotate joint 4 by 30 degrees means absolutely nothing to a robot that doesn't have a joint 4.
Or where joint 4 controls a wheel instead of an elbow.
Exactly. The skill remains entirely trapped inside the original robot's form factor. We just assumed that the transfer of knowledge depended entirely on likeness. Same form, same training, same operating system.
And this philosophy of sameness, it extends so far beyond just engineering.
Yeah.
If we pull this back to human terms, it's like trying to teach a friend how to cook a highly specific, complex dish, say a perfect risotto.
Oh, that's a great example. Risotto is tough.
It is. And if you were forced to teach them, using the old robotics paradigm, you couldn't just give them the recipe or explain the chemical processes.
No, you have to stand behind them and physically manipulate their body.
Exactly. You would literally force them to hold the wooden spoon at the exact angle you hold it, stir at your exact velocity, and stand at your exact distance from the stove.
Which would be disastrous. I mean,
Yeah.
if your friend is 6 inches taller than you...
Or left-handed.
Right, or left-handed, or just has a different center of gravity, forcing them to mimic your biomechanics will actually hinder their ability to cook the dish.
They'd be so intensely focused on replicating your wrist angle that they wouldn't notice the garlic burning.
Exactly. They miss the actual goal because they're hyper-fixated on the kinematic motion.
Right. But the way we actually teach a human being how to make risotto is by conveying the intention behind the actions.
Yes, the high-level goal.
We explain the state change we're looking for. We say, you need to sweat the onions until they are translucent, or you need to add the broth slowly and agitate the rice until it releases its starches and becomes creamy.
We provide a high-level semantic goal. And then we just trust their brain to calculate the lower-level kinematics required to execute that goal using their specific body and their specific tools.
We allow them to abstract the intention from the physical action. And in humans, this abstraction happens so seamlessly we don't even realize we are doing it.
We do it every day. But in machines, the inability to do this creates what is known as translation overhead.
Translation overhead.
Yeah.
The paper highlights this concept really heavily.
It does. When the gap between physical forms, the embodiment gap we mentioned earlier, when that grows too large, collaboration or skill transfer devolves into translation overhead at best.
And complete system failure at worst.
Exactly.
Let's define translation overhead computationally, because it's not just some minor inconvenience, right? It's a massive barrier.
It's huge.
It essentially means that a machine is burning an unsustainable amount of its processing power just trying to translate foreign instructions into something it can physically execute,
Right.
rather than actually just doing the task.
Think about the computational friction involved there. If a bipedal humanoid robot wants to hand a task off to a quadruped robot, so a robot that looks like a dog, it can't just pass over its control policy.
Because the dog doesn't have arms.
Right. Engineers have historically had to build these massive, complex transformation matrices to map the humanoid's gait and balance parameters onto the quadruped's 4 legs.
That sounds like a nightmare to code.
It's like a pianist trying to teach a drummer how to play a piece of music by explaining the exact pressure applied to the piano keys.
But the drummer has sticks, not keys.
The mapping is categorically mismatched. By the time the system calculates how a shoulder rotation correlates to a knee joint, the processing latency is so high that the robot literally falls over in real time.
The overhead is fatal. The assumption of sameness breaks down the exact moment it encounters the reality of physical difference.
And that brings us to the actual breakthrough published in Science Robotics.
Yes. Let's get into the fix.
The researchers basically realized that trying to map joint angles between unlike bodies was a total dead end. They needed to stop asking, do we move the same? And start asking, do we understand the same aim?
And their solution is this framework called Intention-Aligned Imitation Learning, or IAI.
IAI is a fundamental departure from that old kinematic mapping. Instead of trying to transfer a file filled with motor velocities and torque values, IAI transfers a high-level representation of what the action is actually for.
It uses natural language intention descriptions to bridge the embodiment gap.
Yes, human language.
Okay, here's where I really need to press you on the mechanics, because the phrase natural language intention description sounds a bit like magic when we apply it to heavy machinery.
I get that. It sounds sci-fi.
It really does. We were talking about using human language words, syntax, semantics, to bridge a physical hardware gap. How does describing an intention in English actually help a machine with hydraulic presses or pneumatic wheels?
It's a very valid question.
Because language is incredibly abstract. A sentence doesn't possess torque. How does an abstract string of text translate into physical manipulation in a three-dimensional space?
That is the exact friction point the researchers had to solve. And the answer lies in vision language action models, or VLA models.
VLAs, okay.
Over the last few years, large language models haven't just been learning grammar. They've actually been building these massive, multidimensional maps of semantic meaning and physical relationships.
So they understand how the world works, not just how words work.
Exactly. When an IIL system operates, it's not just reading a sentence, it's looking at a visual scene, parsing the objects within it, and using language as an intermediate bridge between the visual input and the physical output.
Okay, walk me through the actual sequence of events here. Let's make it concrete. Let's say we have robot A, which is a robotic arm with a multi-fingered hand.
Okay.
And we have robot B, which is just a mobile base with a single rigid suction cup. Radically different bodies.
Right. Under the IALL framework, Robot A performs a task. Let's say it opens a sliding cabinet door. It uses its fingers to grip the handle, pulls laterally, and slides the door open.
Okay, a human could do that easily.
A vision model observes this robot doing it, but instead of recording the joint angles of the fingers, the model analyzes the initial state of the environment and the final state.
It looks at the before and after.
Yes. It extracts the semantic goal. It generates a natural language description. The intention is to transition the sliding cabinet door from a closed state to an open state.
Wow. So it strips away all the specific physical constraints. It totally decouples the goal from the agent.
Completely.
The sentence, transition the door to an open state, doesn't dictate how to do it.
Yeah.
It just dictates the desired reality.
Exactly. That pure intention encoded in language is then handed over to Robot B, the machine with the suction cup.
Who doesn't have fingers?
Right. Robot B receives the intention. Its own onboard VLA model looks at its own physical affordances, like what its body is mathematically capable of doing, and it looks at the cabinet.
And it realizes, I do not have fingers to grasp a handle.
But it says, however, I have a suction cup that can adhere to a flat surface, and I have wheels that can move laterally.
Oh, wow. So it generates a completely novel physical policy on the fly to achieve the semantic goal.
Yes. It adheres the suction cup to the glass of the door, completely ignoring the handle, and drives to the left, sliding the door open.
It re-expresses the aim through its own unique physical form.
Yeah.
That is incredible.
Language acts as the universal translator here. It serves as an abstraction layer that sits above the hardware. But to address your point about the mechanics, how language actually becomes torque, we have to look at how these systems handle latency and control.
That's a crucial point, yeah. Because large language models are notoriously slow compared to physical reflexes.
Very slow.
It can take an LLM a couple of seconds to generate a sentence. But if a robot is carrying a glass of water and hits a bump, it needs to adjust its balance in milliseconds.
Has enough seconds to think.
Right. You can't have an LLM pausing to generate a paragraph about gravity while the robot is literally falling over.
Which is exactly why the architecture is hierarchical. The natural language intention doesn't directly control the motors.
Oh, it doesn't?
No. The system operates on two distinct loops. The high-level loop, which is driven by the VLA model, runs relatively slowly. It assesses the scene, understands the intention, and generates what's called a spatial reward function.
A spatial reward function.
Yeah. It essentially says, the goal is for this door to be over there. Any action that moves the door closer to that state is good. Any action that moves it further away is bad.
Ah, okay. So it translates the language into a mathematical gradient, like a map of good and bad states.
Precisely. And then it hands that reward function down to the low-level control loop.
The fast loop.
Yes.
Yeah.
This low-level loop, usually driven by model predictive control or highly optimized reinforcement learning policies, runs at hundreds of hertz, hundreds of times a second. It handles the raw physics, it calculates the necessary torque, manages the friction of the wheels, and adjusts for balance in real time, constantly trying to maximize the reward function set by the language model.
So the LLM dictates the what at a high level, and the low-level controller figures out the how at blistering speeds.
That's it exactly. That separation of concerns is brilliant. It completely bypasses the translation overhead that used to crash these systems.
And this wasn't just tested in a vacuum, right? The scale of the study published in Science Robotics is what really validates the theory.
They didn't hold back. They tested IAL across 7 distinct robot embodiments, operating in 30 completely different scenarios.
7 bodies, 30 tasks.
And the diversity of the hardware was very intentional. They didn't just use 2 slightly different robotic arms. They used quadrupeds, wheeled bases, 7-degree-of-freedom manipulators, parallel grippers.
A total menagerie of robots.
Yeah, and the scenarios ranged from simple pick-and-place tasks all the way to complex navigation and articulation tasks. By successfully transferring skills across this wide of a physical spectrum, they empirically proved that intention can function as a universal adapter.
It fundamentally changes what it means for machines to learn from one another. The Science Robotics paper is explicit about this. What matters is no longer sameness of form, but alignment of intention.
And that takes us directly into the real-world implications.
Because this isn't just about making cooler videos of robots in a lab for YouTube.
No, the source material explicitly points to fields like mixed fleets, industrial automation, elder care, and mobility systems.
These are industries that are currently bottlenecked by the inability of diverse machines to coordinate.
Let's look at industrial automation first. Right now, a modern factory floor is incredibly segregated.
It really is.
You might have an assembly line run entirely by QCO robotic arms, and then a logistics area run by Boston Dynamics mobile robots, and a packaging area run by Universal robots.
And they cannot talk to each other. They operate in completely siloed ecosystems.
It's the ultimate vendor lock-in.
Yeah. If a factory wants to optimize a process that spans across all 3 areas, it requires human engineers to manually write custom integration software to bridge the gap between these entirely different operating systems and kinematic models.
Which is expensive and slow, but with intention-aligned imitation learning, that vendor lock-in begins to dissolve.
Because they speak the same high-level language.
Right. If the systems are communicating via intention, the factory's central AI can issue a single high-level command. Maintain a steady flow of material to the final assembly station.
And that's it.
That's it. The mobile robots, the robotic arms, and the packaging machines receive that shared intention and autonomously adjust their specific physical actions to meet the goal.
So the wheeled robot speeds up its delivery route, the arm adjusts its grasping strategy to handle the increased throughput.
And they coordinate not by sharing code, but by sharing aim.
A wheeled robot does not need to become an arm. A silicon intelligence does not need to become a human. That quote from the text really solidifies the practical application for me.
It's a great summation.
But the application that I think resonates most deeply on a human level, for you listening, think about how this affects our daily lives, is elder care.
Oh, absolutely. The elder care scenario is perhaps the most profound use case because it deals with highly unstructured, unpredictable environments where safety is paramount.
Let's paint a picture of what that looks like based on this breakthrough. Imagine a patient's room in an assisted living facility in the near future.
Okay.
The care isn't being provided by a single, expensive humanoid android trying to do everything like cooking and lifting and monitoring.
That's usually what people picture, like a robot butler.
Right, but that's wildly inefficient. Instead, the patient is supported by a highly specialized, diverse ecosystem of machines, what the industry calls a mixed fleet.
A mixed fleet.
You might have a smart bed, which is essentially a low-profile robot designed to adjust posture, monitor pressure points, and track vitals. You have a wheeled cart robot that navigates the hallways to fetch water or transport medication.
Very different machines.
And maybe you have a soft robotics lifting mechanism mounted to the ceiling to safely assist the patient in standing up.
Okay, so under the old paradigm, getting those 3 highly dissimilar machines to orchestrate a complex care routine would be an absolute nightmare.
Because they speak different languages.
Right. The smart bed only understands tilt angles and pressure sensors. The cart only understands 2D spatial mapping and object avoidance. The ceiling lift only understands tension and payload. They have completely different affordances.
But with IIL, they don't need a unified kinematic language. The central care system observes that the patient is restless and dehydrated. It issues a natural language intention. Ensure the patient is comfortable and hydrated.
Just that one sentence.
That single aim is broadcast to the entire fleet.
And this is where we see the power of decentralized execution.
How does it play out?
Well, the smart bed receives the intention, senses a pressure buildup on the patient's lower back, and gently adjusts its tilt to alleviate it, effectively expressing the intention of comfort.
Beautiful.
Simultaneously, the wheeled cart receives that same intention, navigates to the dispenser, fills a cup of water, and brings it to the bedside, expressing the intention of hydration.
And the ceiling lift.
The ceiling lift remains on standby. It senses no immediate need for tension, but it prepares its reward function just in case the patient decides to sit up to reach the water.
They are acting as a cohesive unit, not because they are alike, but because their differences are newly workable under a shared aim.
Making difference newly workable. That phrase from the text is the crux of this entire conversation.
Historically, in both technology and society, we have treated difference as a hard barrier to collaboration. If you were fundamentally different from me, different hardware, different background, different language, we couldn't work together efficiently unless one of us compromised and learned to operate exactly like the other.
And historically, let's be honest, that compromise is never equal.
Never.
The entity with less power, less compute, or less social capital is always forced to conform to the dominant entity's way of doing things.
The wheeled robot is forced to try and interpret the arm's commands.
The minority is forced to assimilate into the majority's cultural norms. The subordinate is forced to adopt the manager's working style.
Exactly. But this framework treats difference not as a barrier to be destroyed, but as a condition under which collaboration simply requires better inference.
It requires us to communicate the why instead of dictating the how.
It's a biological approach, really. If you look at how humans and working dogs coordinate on a hunt or a search and rescue mission, they don't share a kinematic language.
No, not at all.
A human cannot track a scent like a bloodhound, and a bloodhound cannot open doors or read maps like a human, but they align their intentions.
The human communicates the goal, find the missing person, and the dog executes that goal using physical affordances the human doesn't even possess.
It is a perfect analog. The human and the dog maintain their unique forms and their unique capabilities while participating in a deeply complex shared goal.
And as the source material makes clear, this brings us to the human mirror.
Because as soon as you elevate the importance of intention in language, you run headfirst into the oldest, messiest, most dangerous problems of human culture.
Oh yeah, we can't just marvel at the technology without acknowledging the profound risks the text warns us about.
This is not a narrow robotics advance, the author states, because intention is not a magic solvent. It doesn't instantly dissolve all the friction of collaboration.
In fact, when we rely heavily on natural language and abstract intentions to bridge differences, we open ourselves up to severe vulnerabilities.
Particularly because language is inherently flawed and ambiguous.
The researchers and the analysts are very clear about the failure modes here. Misread aims can wildly distort action. Language can be incredibly vague.
And the most piercing critique in the entire text is this: shared goals can hide unequal power.
That sentence is a gut punch.
It really is. Humans are experts at claiming common purpose while pursuing very different things. We really need to unpack this carefully, because this is where the robotics breakthrough perfectly encapsulates human sociology.
Okay, so in a machine context, if two robots share a perfectly defined intention, they will mathematically pursue it to the best of their physical abilities. There is no deceit.
Right. A robot isn't going to lie to you about wanting to open the door.
But in the human world, language is rarely perfectly defined. It is subjective, it's context-dependent, and heavily influenced by the speaker's hidden motives.
We frequently use shared abstract language not to clarify our goals, but to mask conflicting desires.
Exactly.
Let me give you an analogy. Think about a massive corporate merger. Let's say a massive multinational conglomerate, Company A, is acquiring a smaller, highly innovative startup, Company B.
A classic scenario.
The leadership of both companies gets up on stage at a town hall meeting and announces a shared natural language intention to the employees and the press. They say, "Our primary goal with this merger is to aggressively increase operational efficiency and streamline the customer experience."
It is a perfectly aligned, high-level intention. On the surface, everyone agrees. I mean, who doesn't want to increase efficiency?
Right. The employees applaud, the shareholders are happy, but because the language of that intention is inherently vague, the translation of that intention into physical action is going to be wildly distorted by whoever holds the power.
And in this case, Company A holds the power.
Exactly. To the executives at Company A, the abstract phrase increasing efficiency mathematically translates into a very specific set of actions. Mass layoffs at Company B, liquidating their redundant departments and absorbing their intellectual property.
But to the engineers and workers at Company B, the phrase increasing efficiency meant something entirely different.
Completely different. Based on their context, they thought the intention meant upgrading their slow internal software, getting larger budgets for R&D, and removing bureaucratic red tape so they could innovate faster.
The intention was completely shared in language, but the execution was completely contradictory.
Company B thought they were participating in a beautifully aligned collaborative goal, but they were actually victims of a misread aim, orchestrated by a power imbalance.
The exact same words resulted in mutually exclusive realities. Shared goals can still hide unequal power.
This dynamic exists in almost every facet of human organization.
How often in history have two nations sat down at a negotiating table, agreed to a natural language intention like maintaining regional security or ensuring mutual prosperity, only to realize a decade later that their respective definitions of those words required entirely opposing physical actions?
It is the defining tragedy of geopolitics. When language is vague, the entity, whether it's a machine or a human institution, will fill in the blanks with its own biases, its own literal interpretations, and its own self-interest.
If an AI is given an ambiguous intention, it might find a mathematically optimal but ethically horrifying way to achieve it.
And if a powerful institution is given an ambiguous mandate, it will interpret that mandate in a way that consolidates its power.
Which is why the source text cautions us so strongly against treating intention alignment as some kind of utopian solution.
Just because we have built a computational bridge across the embodiment gap doesn't mean that bridge is inherently safe to cross.
It demands an incredibly high degree of rigor, honesty, and clarity in how we define our aims.
The less precise the language, the more room there is for the dominant form to impose its will under the guise of cooperation.
And this naturally leads us to the philosophical climax of the source material.
Yes. The researchers didn't just solve a kinematic problem. They used this entire framework to propose a completely new definition of intelligence itself.
It is a radical proposition. For all of human history, and certainly for the history of artificial intelligence, we have implicitly defined intelligence through the lens of mimicry.
We measure how perfectly one form can reproduce the outputs of another.
We see this everywhere.
In our education system, rote memorization is often rewarded above all else. The student who can perfectly regurgitate the teacher's lecture notes onto the exam paper is deemed the most intelligent.
In the corporate world, the employee who perfectly mimics the working style, the jargon, and the mannerisms of the CEO is the one tapped for leadership.
We have traditionally measured intelligence by the accuracy of the reproduction.
But the science robotics paper, in the analysis of it, throws that assumption out completely. Mimicry is not intelligence. Mimicry is overfitting to the training data.
Overfitting, that's a great way to put it.
If you can only succeed by copying exactly what has been done before, you are completely fragile in the face of a novel situation.
The text proposes a far more robust definition. Let me read the exact standard laid out in the analysis.
Please do.
It says, intelligence is better measured by how cleanly an aim can travel across difference without collapsing into noise, domination, or false sameness.
How cleanly an aim can travel across difference without collapsing into noise, domination, or false sameness. That is a dense, challenging metric.
Let's break down those three specific failure states because they map perfectly onto the ways our own communications break down every single day.
Okay, the first failure state is noise.
Noise.
In information theory, specifically Claude Shannon's formulations, noise is entropy. It is the degradation of a signal as it passes through a medium.
So if an aim collapses into noise, it means the signal was lost in translation because the embodiment gap was too wide and the inference was too poor.
In a robotics context, this is what happens when the high-level intention is simply too abstract for the low-level controller to map to its physical affordances.
You tell a wheeled robot, navigate the stairs.
Yeah.
And because it literally lacks the physical mechanisms to process that geometry, it just spins its wheels in confusion until the battery dies.
The aim degrades into useless, chaotic action.
In human terms, an aim collapsing into noise happens constantly in cross-disciplinary work.
All the time.
Imagine a highly technical back-end software engineer trying to explain the necessity of database normalization to a purely visual graphic designer. or vice versa.
If they cannot find a shared abstracted language of intention, if they insist on using the highly specific jargon of their own embodiments, the collaboration devolves into endless, frustrating email chains.
Misunderstandings compound. Timelines stretch. The project aim collapses into the noise of miscommunication.
The second failure state is domination. And we touched on this earlier, but it is vital to explicitly define it as a failure of intelligence.
Domination is the regression to the old paradigm. It is the refusal to let the aim travel across difference at all.
Instead of doing the hard computational or cognitive work of translating an intention, the more powerful entity simply forces the other to adopt its own physical or operational form.
It demands, I will not translate. You must mimic me.
It is the ultimate rejection of difference. It's demanding the wheeled robot somehow grow arms.
It's the historical practice of forcing left-handed children to write with their right hands, completely ignoring their natural biomechanics.
It is cultural imperialism disguised as standardization. Sure, you might ultimately achieve a goal through domination, but you do so by violently erasing the unique capabilities and efficiencies of the other party.
It is not a collaboration, it is subjugation. And according to this new metric, it is a hallmark of low intelligence.
Which brings us to the third and arguably the most insidious failure state, false sameness.
False sameness, the illusion of common purpose.
Yes. False sameness occurs when both parties maintain a polite facade of perfect understanding, explicitly to avoid the difficult, messy work of actual translation.
They pretend their embodiments or their contexts are identical when they're fundamentally at odds.
Going back to our corporate merger analogy, false sameness is the executives and the engineers all nodding vigorously at the phrase increasing efficiency.
Each secretly knowing they define the term differently, but refusing to clarify it because clarifying it would cause immediate conflict.
They hide behind the ambiguity of language.
In machine learning, false sameness is a phenomenon known as semantic drift, where a model technically aligns with a human prompt, but executes it in a way that violates unstated human values.
The machine nods along, pretending it understands the human context, and then pursues the goal with catastrophic literalism.
False sameness is dangerous because it delays the inevitable friction of difference until the absolute worst possible moment, the moment of action.
So if we synthesize all of this, true intelligence, according to this new framework, is the ability to navigate between those three traps.
True intelligence is looking at someone, or something, that possesses a fundamentally different architecture, a different background, a different set of physical or cognitive affordances.
It is the ability to communicate a clear, unambiguous goal, and then crucially trusting them to achieve that goal using their own unique methods.
It is succeeding without degrading into the noise of confusion, without exerting the domination of forced mimicry, and without hiding behind the cowardice of false sameness.
As the text aptly notes, that is a harder standard, and a better one. It requires significantly more processing power, both computationally for machines and cognitively for humans.
So what does this all mean for you listening to this deep dive? Think about this in the context of your own life, your own workplace, your own relationships.
It's a mirror.
If we apply this harder, better standard to ourselves, we have to ask some deeply uncomfortable questions about how we interact with the people around us. When you try to teach a colleague or communicate with a partner, are you demanding false sameness? Or are you actually letting your aim travel across your differences?
When you are managing a team, are you guilty of domination? Are you demanding that they organize their digital files exactly the way you do, or approach problem solving with the exact same mental models you use simply because it validates your own way of working?
We constantly conflate the how with the what. We demand people process stress or communicate affection or execute projects exactly the way we do because it makes us feel secure.
It makes us feel like our specific embodiment is the correct one.
But in doing so, we dramatically limit the potential of the collaboration. If you force a brilliant, highly creative lateral thinker to operate within the strict, linear spreadsheets of a highly analytical manager, you're demanding mimicry.
You are creating massive translation overhead in that employee's brain, and you are leaving all of their unique, diverse capabilities on the table.
If instead we can let go of the how and rigorously, honestly define the what, we open ourselves up to efficiencies and solutions we could never have engineered ourselves precisely because we are locked inside our own specific perspectives.
And this is the immense value of studying these technological breakthroughs. We started this discussion looking at the kinematics of a few robots in a university lab, trying to figure out how to pass a block from a gripper to a suction cup.
Right.
But because of the fundamental nature of the problem they were solving, the problem of difference, we ended up with a profound sociological framework for human relationships, power dynamics, and organizational behavior.
It is genuinely awe-inspiring how a robotics paper essentially wrote a profound sociological theory.
It shouldn't be entirely surprising, though.
Why not?
As we build increasingly complex systems that perceive, decide, and act in the physical world, those systems will inevitably reflect the deepest structural realities of our own existence.
The barriers engineers are trying to overcome in robotics today, the friction of translation, the ambiguity of language, the integration of diverse forms, are the exact same barriers human societies have been violently struggling against for millennia. So, let's synthesize the incredible journey of this deep dive. We started with 7 robots learning via intention-aligned imitation learning in a lab and ended with a fundamental rethinking of skill, teaching, collaboration, agency, and understanding.
It's been quite a ride.
The source material, The Portability of Intention, argues that we are standing on the precipice of a new era of interaction. The old bottleneck of likeness, the rigid demand for exact physical mimicry in shared form, is technically and philosophically breaking down.
We have empirically proven that skill, teaching, and complex coordination do not require us to share an architecture. They require us to share an aim.
And as the analysis concludes, navigating this reality may turn out to be one of the central tasks of the coming decades.
The central challenge is no longer about how to force unlike beings, whether they are diverse machines, diverse cultures, or diverse minds, into a standardized sameness.
The challenge is learning whether a deeply held common aim can remain intact, safe, and unambiguous while each entity expresses that aim in its own entirely unique way.
Making difference newly workable.
It is a beautiful phrase, but as we've seen, it is a monumental, precarious challenge. Because if we can achieve that level of intention alignment without falling into noise or domination, as the text points out, that would be a very different kind of cooperation.
It would be a cooperation based on the maximization of unique affordances, rather than the forced homogenization of behavior.
As we wrap up, I want to leave you with one final, lingering concept to mull over. We spent this time exploring the beauty and the difficulty of an intention traveling cleanly across difference. But let's take that concept and push it to its extreme logical conclusion. Let's look slightly beyond the immediate scope of the paper.
Extrapolating the timeline. I like it.
If intention truly becomes completely portable across any physical or digital form, whether it's a small-wheeled robot, a massive distributed AI network controlling a city grid, or an entirely alien quantum-based machine architecture we haven't even invented yet, what happens when the embodiment gap is so vast that the execution of the intention becomes unrecognizable to us?
You mean, what happens when the how becomes so bizarre, so completely decoupled from human biomechanics or human logic, that we lose the ability to perceive the what?
Exactly. What if, 10 years from now, we assign a highly advanced citywide AI system a clear, natural language intention, ensure that vehicular traffic flows with maximum efficiency and 0 fatalities? The AI receives the intention, maps its massive distributed affordances, and begins to execute. But the method it chooses looks like absolute, terrifying chaos to human eyes.
Like cars weaving within inches of each other.
Yes. Imagine cars weaving within inches of each other at 80 miles an hour, traffic lights flashing in seemingly random, chaotic patterns, pedestrian crosswalks shifting dynamically by the second. To a human observer, it looks like a system completely out of control. It looks like madness.
But mathematically, the intention is being met perfectly. There are 0 accidents, there are 0 wait times, throughput is maximized.
The intention is perfectly fulfilled, but the physical expression of it induces panic because it completely defies human kinematic expectations.
It's totally alien to us.
Right. If the action looks completely foreign, but the aim is demonstrably met, will we have the wisdom to accept it? Or will we panic and pull the plug simply because we don't understand the physical movements?
Will we still instinctively demand that the machines look like us, drive like us, and solve problems like us?
Will we still hover over them, demanding they hold a pencil exactly the way we taught them, even if they are already writing a masterpiece? It is a question that challenges the very core of our ego as creators. Thank you so much for joining us on this deep dive. We'll catch you next time.